1. What is Kubernetes? Kubernetes is an open-source system for automating deployment, scaling, and management of containerized applications. 2. What are the benefits of using Kubernetes? Benefits include simplified deployment, scaling, self-healing capabilities, and high availability. 3. What is the difference between Docker and Kubernetes? Docker is a containerization platform, while Kubernetes is a container orchestration platform that manages the lifecycle of containers across multiple hosts. 4. What are the main components of a Kubernetes cluster? Master, API server, scheduler, controller manager, manages the cluster and schedules workloads. Worker nodes, kubelet, kubeproxy, run containerized applications. 5. What are the different types of Kubernetes resources? Pods, groups one or more containers and shared storage. Deployments, manage the desired state of pods. Services, expose pods to external traffic. 6. Explain the difference between deployments and replica sets. Deployments manage rollouts and rollbacks of updates, while replica sets ensure a specific number of pod replicas run. 7. How do you scale a deployment in Kubernetes? You can scale deployments by adjusting the desired number of replicas. 8. What are some best practices for deploying applications in Kubernetes? Use namespaces for logical grouping, leverage declarative configuration, implement rolling updates for minimal downtime, and consider container security. 9. What are some common troubleshooting steps for pods that are not running? Check pod logs, events, and resource requests/limits. Verify node health and available resources. Use kubectl commands to inspect the state of pods. 10. How do you handle a node failure in Kubernetes? Kubernetes automatically reschedules pods on healthy nodes. Utilize liveness and readiness probes for automated restarts of failing pods. 11. What are different types of Kubernetes services? Cluster IP, internal cluster access. Node port, exposed on all nodes. Load balancer, external load balancing. External name, map service to an existing DNS name. 12. What are ingress resources used for? Ingress resources configure how external HTTP/HTTPS traffic reaches services within a cluster. 13. Explain the concept of namespaces in Kubernetes. Namespaces logically isolate resources for different projects or users within a cluster. 14. How do you secure your Kubernetes cluster? Implement authentication and authorization mechanisms, RBAC. Utilize secrets management for sensitive data, enforce pod security policies, and regularly monitor for vulnerabilities. 15. Explain the concept of least privilege in Kubernetes. Grant pods and service accounts the minimum permissions required to perform their tasks, minimizing the attack surface. 16. How does Kubernetes handle network traffic between pods? Pods within the same network namespace can communicate directly, while interpod communication across namespaces requires service exposure. 17. Describe different strategies for exposing applications running in Kubernetes externally. Utilize node port, load balancer services, or ingress resources depending on your specific requirements and network configuration. 18. How do you provision persistent storage for stateful applications in Kubernetes? Leverage persistent volumes, PVs, and persistent volume claims, PVCs, to abstract storage provisioning and management. 19. Explain the differences between different storage classes in Kubernetes. Storage classes define the capabilities and provisioning options of storage resources for your pods. 20. Describe how liveness and readiness probes work in Kubernetes. Liveness probes determine if a container is healthy and needs to be restarted. Readiness probes determine if a pod is ready to receive traffic. 21. How do you handle horizontal pod autoscaling, HPA, in Kubernetes? Use HPAs to automatically scale deployments based on predefined metrics like CPU or memory utilization. 22. Explain the concept of custom resource definitions, CRDs, in Kubernetes and their use cases. Answer. CRDs extend the Kubernetes API to manage custom resources specific to your application or environment. They allow you to define the desired state and life cycle of these resources, enabling them to be managed alongside other native Kubernetes resources. Use cases include managing configuration for databases, monitoring tools, or application-specific deployments. 23. How do you handle secrets rotation in a Kubernetes cluster effectively? Answer. Implement automated secrets rotation strategies. Use tools like Sealed Secrets or KMS, Key Management System integration. These tools encrypt secrets before storing them in Kubernetes and manage their rotation without downtime. Leverage environment variable injection. Inject secrets as environment variables into pods at runtime, allowing for updates without modifying container images. Utilize pre-built solutions. Consider managed services like AWS Secrets Manager or GCP Secret Manager for centralized secret management and rotation. 24. Describe your approach to monitoring and logging in a Kubernetes environment. Answer. Choose a monitoring tool. Popular options include Prometheus, Grafana, and Datadog, offering metrics collection, visualization, and alerting capabilities. Integrate with Kubernetes APIs. Use tools that scrape metrics directly from the Kubernetes API server to monitor cluster health and pod performance. Utilize sidecar containers. Deploy sidecar containers alongside application pods to collect logs and forward them to a centralized logging platform like Elasticsearch or Loki. Configure log scraping and aggregation. Define log scraping rules and aggregation pipelines to efficiently manage and analyze application logs. 25. Explain the benefits and challenges of using stateful applications in Kubernetes. Answer. Benefits. Improved scalability and resource management. Kubernetes facilitates scaling stateful applications horizontally and managing their resources effectively. Simplified deployments and rollbacks. Declarative configuration and rollouts minimize downtime and complexity during updates. Increased availability. Kubernetes offers self-healing capabilities and rescheduling of pods on node failures. Challenges. Data persistence. Stateful applications require persistent storage solutions like persistent volumes, PVs, and persistent volume claims, PVCs, to manage data across pod restarts. State management complexity. Maintaining state consistency across multiple pods and potential scaling scenarios requires careful design and implementation. Operator complexity. Stateful applications might require custom operators to manage their lifecycle and specific needs within the Kubernetes environment. 26. How do you approach disaster recovery, DR, for your Kubernetes deployments? Answer. Back up your cluster state. Regularly back up your cluster state, including configuration, resources, and persistent volumes, using tools like Valero or KubeADM for disaster recovery. Utilize multi-region clusters. Consider deploying your cluster across multiple regions or zones to improve fault tolerance and geographically disperse your applications. Design for rapid recovery. Plan your DR strategy, including rollback procedures, network configuration, and disaster recovery testing to ensure a swift recovery process. 27. How do you approach security best practices for deploying containerized workloads in a Kubernetes environment? Answer. Implement role-based access control, RBAC. Define granular access permissions for users and service accounts within the cluster to minimize the attack surface. Use security contexts. Configure security context, for pods to restrict their capabilities and privileges within the cluster. Scan container images for vulnerabilities. Integrate vulnerability scanning tools into your CE/CD pipeline to identify and address potential security issues in container images before deployment. Monitor cluster activity. Implement continuous monitoring of your cluster for suspicious activities and potential security threats. 28. Explain the concept of kube server and its role in a Kubernetes cluster. Answer. The kube server, also known as the Kubernetes API server, is the central component of a Kubernetes cluster. It acts as the single point of entry for all API requests and serves as the control plane for managing cluster resources. Key functionalities include providing the RESTful API, enables interaction with the cluster and management of resources through tools like kubectl or code integration. Resource validation and admission control ensures resource requests comply with defined policies before persisting them in the EKT data store. Coordinating cluster activities communicates with other control plane components, scheduler, controller manager, to maintain cluster state and orchestrate deployments. 29. Describe the different types of Kubernetes controllers and their functionalities. Answer. Kubernetes controllers are responsible for continuously monitoring the state of the cluster and ensuring it aligns with the desired state specified in your configurations. Some key controller types include replication controller, ensures a specific number of pod replicas are running for a deployment. Deployment controller manages the rollout and rollback of pod updates for deployments in a controlled manner. Stateful set controller guarantees a certain number of pods are running in a specific order and ensures their persistent storage even during restarts. Horizontal pod autoscaler HPA controller automatically scales deployments based on defined metrics like CPU or memory usage. 30. How do you achieve high availability for the Kubernetes control plane itself? Answer. While Kubernetes offers self-healing capabilities for worker nodes, the control plane itself requires additional considerations for high availability. Run the control plane components, API server, EKT, scheduler, controller manager, across multiple nodes in a highly available configuration. Utilize tools like HAProxy or kube server to manage failover and load balancing between control plane nodes. Implement EKT clustering. Utilize EKT clusters with multiple members to ensure data consistency and availability even if some members fail.